All right, so as before being the last couple of weeks, your homework is the last slide of these set of slides that I will send out today, like I did before. I'll actually get them posted on our digital classroom, which reminds me, before we leave, I need to grab the slips of paper. I have your little note cards that you gave to me. I have a note of encouragement on them, and I have your username and password to access our digital classroom, where you can access materials. So somebody please remind me to grab that before we leave. I'm sorry about last week. I was fully anticipating being back, but did I tell you all we have 2 foster kids right now? And so I had to have a support team meeting with the parents, the foster parents, and I thought I would be able to make it back in time, and I wasn't able to. So Dr. McLean graciously stepped in, but I know he doesn't know my full vision for what this is, so no matter how good of a job he does, which he was a student of mine, so I'm sure he did a great job, but it's just not going to be, of course, the same because he doesn't know my full vision for what I want this course to be. So what I want to do today, I want to do another problem together from what you all were working on last week, 2-dimensional projectile motion problems, and then we're going to talk about Newton's laws of motion, right? I also have a quiz for you, but I don't have it quite ready yet, so I will send it with the other materials. And I'll talk more about that once more people start to come. So let me pray for us, and then we'll get started. Father, I thank you for the opportunity that we have to come before you in prayer. I thank you that you are both an all-powerful, incredible creator, but also a loving, personal God. I thank you for that. And I pray that as we are reminded of that we would be encouraged and we would be in awe of just the great privilege it is to know and be known by our Creator. And Father, we ask these things in the name of Jesus. Amen. All right, so projectile motion. What should be, hello, welcome. What should be a review from last week, although again, Dr. McLean does not have the full vision, my full vision of what I want this class to be. So just to kind of work through this together. And as with the slides from a couple of weeks ago, I will send you these with it all worked out on the slide. So we'll work it out together, and then I'll give you another copy of this. So if a basketball is shot from the free throw line at an angle of 35 degrees and a velocity of 25.0 meters per second, how far will it travel horizontally? Assume the ball is shot from a height of 2.00 meters. Okay, so first question we have to answer is, what do we have? Right? What do we have, or what does the problem give us? And what are some of the values or measurements that we're getting? Let's start with the last number given, the height of 2.00 meters. What is that in terms of what we've talked about before? What value is height? We know why not, right? Why not is our initial position vertically. Do you agree? So if our height is 2.00 meters, our why not is 2.00 meters, right? We know our initial velocity, so we know V naught. It's equal to 25.0 meters per second, right? We know our angle is equal to 35 degrees. And that's all we're given. Do you agree? So we have a Y naught, we have a V naught, and we have our angle. Right? Okay. So then what tools do we have? Well, we know that Y at any given time is equal to Y naught plus V naught times T, right? Minus 1/2 GT squared. Right, we know that. And we know that G is equal to 9.80 meters per second squared. Right? These are some of the tools that we have. We also know we have an equation for horizontal position. Right? X is equal to v naught times t. Right? Our position x at any given time is equal to our initial velocity times the amount of time it travels. Do you agree with all this so far? It's okay? And so then it's a question of what do we want? Well, this problem is asking us how far will the ball travel horizontally? And what is that with our tools? What are we looking for? Y is vertical, so vertical position. So horizontally, yeah, we're looking for x. This is how far it's going to travel horizontally. Okay? Do we already know our initial velocity? We do, right? And with our angle, we can know exactly how much of this velocity is going horizontally and how much is going vertically, right? So this v naught would actually be v naught times the cosine of our angle, right? Do you remember doing that? So that's exactly how much of it is going horizontally. This v naught is what?
V naught sine.
Times the sine of 35 degrees. Right? So they're not exactly the same v naught, but they are still v naught, right? We'd have to change it a little bit to figure out how much of it is horizontal, how much of it is vertical. So we know this. Do we know this? We don't. We don't know t. So we want x, but we actually have two unknowns here. We don't know what x is. We don't know what t is. Right? How do we solve for t? Well, if you knew what x was, you could, right? If we knew what x was, we can plug that in for x and we could solve for t. But the thing is, we're going to have to use this formula here to solve for t. And do you remember we do it by graphing? We can estimate t. We can estimate how long the ball's going to remain in the air by graphing this, right? So we don't have to do any complicated algebra. Not to say that it's easy to do that. It's not. There's still some algebraic manipulation, but it's not really complex stuff. You don't have to use anything beyond pre-algebra to do it. Again, it's not saying that that makes it easy. It's just, it's doable without having done a pre-calculus class. Come on in, come on in. It's okay. Okay, so we want x, but first we need to find t. And so we want x, but we need t. And we're going to estimate t by graphing this. Okay, so we're going to graph it. We're going to get an estimate for t, and then we can plug that into here and figure out x. Okay? So remember, when we're graphing a problem like this, we use our formula that our position y is equal to y naught plus v naught times t. But remember, that v naught is actually v naught times the sine of 35, right? Because it's only our velocity vertical. Do you agree? Y is a vertical measurement, so we only want our vertical velocity. So it's y naught plus v naught times the sine of 35 times t minus 1/2 9.80 meters per second squared times t squared. You okay with the modifications I made to our formula? We just changed v naught into v naught times the sine of 35 because we only want vertical velocity. And we put 9.80 meters per second squared in for g. Okay. What is y naught? That was one of the things we have already, right? What is y naught? 2.00 meters. And so now if we're going to graph this, we want to figure out y when t is 0. We want to figure out y when t is 1. We want to figure out y when t is 2, so on and so forth until we can get an estimate for t. Do you remember that? Is this okay? So if t is equal to 0, we know that this is all going to cancel out, right? If you put a 0 in here, 0 times anything is 0, right? If you put a 0 here, this is going to cancel out. Would you agree? 0 times anything is 0. So if t equals 0, what is y equal?
2 meters.
2 meters. Let's keep our keep our precision. So we'll say 2.00 just so we don't lose any of that precision. We want to hold on to it. We want to grasp it. It's important. We love it. I love it. And if I love it, you love it, right? Because that's how things work. Okay, what about if t is equal to 1? So if we put 1 into here, okay, then we're going to get, I guess we could also put our V naught. What's V naught? 25.0 meters per second. Right? You okay with that? We just replaced our V naught with what we were actually given, what we have V naught to be. Okay, so if we put a 1 in for here, where it's basically going to be 25 times the sine of 35. I don't know the sine of 35 off the top of my head. So 35, the sine of 35 times 25. This is now going to be 14.34 meters per second. Okay, if you do 25 times the sine of 35. What is 1 squared? What's 1 times 1? Just 1, right? So this would just be minus 1/2 times 9.8 meters per second. But this is actually 1 second. Sorry, I left off the units. That was bad of me. I keep doing that. I told you, first time we started solving problems together, don't leave off the units. And then what did I do? I left off the units. I'm sorry. So this second is actually going to cancel with this. See, that's why you don't leave off the units, because then I presented units here that aren't true. It's not 14.34 meters per second, it's just 14.34 meters, right? Because seconds cancel. We're multiplying seconds, and then we're dividing it away. Right? You take away 3, you add 3 back, you've got nothing. Do you agree? Right? You have $10. I say you have to split that $10 5 ways. You're like, okay, well, I'm going to split it into 5 piles of $2, right? Now I tell you, okay, well, now take that $2 and multiply 5 back. You're right back at 10, right? So if you divide something away and multiply it. Okay, so seconds squared are going to cancel, right? Seconds squared, we're multiplying it in, we're dividing it away. So here we'd be left with 1/2 times 9.80, which is 4.90 meters. Okay, so we have 2 plus 14 meters minus 4.9 meters. See that? And I should be able to do that in my head, but I can't. And so we get that in this situation, y is equal to 11.44 meters. So after 1 second, the ball is 11.4 meters off the ground. This ball's going to travel a long way. I had this guy, I didn't think about this realistically. This guy just chucked this basketball. What are you going to do? Okay, so now what do we do? Have we gotten to 0 yet? No, we're on the rise, right? The ball started at 2 meters, now it's all the way up to 11 meters, which would be like 35 feet off the ground. So this guy, I mean, he really did just chuck this ball. That's what happens when you make up your own problems, right? They don't often make sense. Okay, what do we do next? Let's try when time is equal to 2, right? So we know what y equals when time is equal to 1. Now we're going to figure out what y equals when time is equal to 2. Go back to our situation here, except for now instead of 1 second, we're going to do 2 seconds. Instead of 1 second squared, we're going to do 2 seconds squared. Okay? The screen's totally in the way there. Sorry. There's a second squared there. Okay? So now it's a little bit different. This is still just going to be 2, but now we're actually multiplying this by 2, right? So 25 times the sine of 35 times 2. Oh wow, that was not right. 35 times 25 times 2. Okay. 28.68 meters. Okay. All I did was basically multiply the number we had before, which was 14.34 0.34 times 2. And then here, now over here, we're still going to get second squared will cancel. And now we have times 40. Okay with that? So we have 1/2 times 9.80 times 4. Which gives us 19.6 meters. So now we have 2 plus 28.67 minus 19.6. Okay with that? So minus 2 and we have y is equal to 11.08 meters. Basically unchanged from what it was before. So we figure out the peak is somewhere in between 1 and 2 seconds. Right. What do we do next? Yeah, we got to keep going until we can get our estimate for time. And again, there are other ways you can do that. If you don't like doing this, you don't like graphing it, you don't like that, I can teach you the complicated algebra to figure out for t. But I like doing this because it gives you good algebraic practice. So we're going to do this for 3. Okay, so now we have 35, the sine of 35, times 25 times 3, which is 43.02 meters. You okay with that? And then this now is 3 squared. What's 3 times 3? 9. So we have 1/2 times 9.80 times 9, which is 44.1 meters. So now we have 2 plus 43.02 minus 44.1. We have y is equal to 0.92 meters. Okay with that? You just plug 3 in. Anybody want to see this worked out a little bit more? Why we got these values? It's okay if you do. Are you okay? See nods, some looks like just they don't care. So we're okay? This we're basically almost to 0. Would you agree? So I would say if you wanted to, you could put t is equal to 4, but we're basically right at 0. Which means that the ball is in the air for approximately how long?
3 seconds.
3 seconds. So t is about 3. Do you agree? Say, now we found t. We want x, but we needed t. We got t. It's about 3. We'll just use t is equal to 3. You okay doing that, using t is equal to 3? So we want x. X is equal to v naught, which is actually v naught cosine x. So it's 25.0 meters times the cosine of 35 times 3 seconds. Meters per second. I put the units, but I put the wrong units. 25.0 meters per second. I'm making a lot of mistakes on you today. I apologize for that. If you want my boo-hoo story, I can tell you I didn't sleep very much last night. You don't care, right? Like, oh, boo-hoo, that's so sad. You're a grown man. Figure it out, right? I get what you're thinking. Now, you guys are way too nice for that. You probably actually would be sad. You're like, oh, man, why didn't you sleep all that well? Because of my son. He shows up in my bed in the middle of the night. Oh, man. So when you do this, where'd my, oh, it's right there in front of my face. The seconds are going to cancel, and you get that the ball travels 61.44 meters, which is like 200 feet. So this guy was standing at the free throw line and shoots the ball under this scenario, basically throws the basketball, 200 feet or so. No big deal, right? No big deal. It's pretty close. I don't even know how far the free throw line is from the basket. It's like 20 feet, 18 feet, 20 feet. Does anyone know? I don't know. I think it's not that far. It's not 200 feet. But alas, that's what happens when you make up a problem. It just doesn't always. You basically launched it out of the Which makes sense, because that velocity is like 50 miles an hour. And I'm sure there are people that can throw a basketball at 50 miles an hour. Is everyone okay with this? So this actually combined a couple of concepts from what you were doing last week. Graphing two-dimensional problems, while at the same time solving for a certain problem. This is a really good problem. And so again, I'll work this out. I'll send you the slides with all this worked out. If you wrote it down, it was great. If you didn't, this is fine. We can get all that settled. All right. Any questions about this? Don't feel like you can't ask questions. I realize that my brain is not working as well as it ought to be right now, and so there could be some really strange things happening. Okay, well we're just going to take that as like everybody's okay, on the same page. Okay, so I mentioned this before, but not everyone was here. I am going to give you a quiz today, but I don't have it quite finished yet, so I'm actually going to send it out when I send out the homework on the slides. It'll just have another slide at the end. So I'll have a slide that says homework, and then I'll have a slide that says quiz. The way your homeworks are graded, which the homeworks from all 3 weeks, I don't know if I mentioned this before about when everything is due, but everything will be due actually in a couple of weeks. So I'll let you all know that too. Last week was crazy. We were going to talk about it last week. I wasn't here. You were. Anyways. But the homeworks, the way they're basically graded is if you attempt the problems, you get full credit, right? Even if you can't solve them all. Although if you can solve them, let me know and I'll help you out. Some of you have done that and have sent me emails and saying like, hey, I couldn't figure out this problem. Could you help me out? And I'm glad to do that. Okay, but the homework problems, if you attempt them, you get the full points. On the quizzes, they're going to work just like the homework. You can complete them even if you want to. You can work through the quiz with a sibling of yours that's in the class. That's fine. But it's not just like, if you attempt it, you're good. Like you also need to have the correct answer. You need to have the correct number or the correct amount of precision. So like this problem here, when you go back and look at this, is there any problem with this level of precision? How many total numbers are we presenting here? 4. There should only be 3, right? So which means we actually have to go back here and eliminate this and say 61.4 meters because we presented too much precision, more precision than we're capable of. Okay, so when it comes time for a quiz, they will be assessed a little bit differently, but you can work on them together. If you work on your homeworks together, that's fine. But it's just you have to kind of have units and all those things. You have to present the right number of significant values and present the numbers properly. When it comes time for an actual exam, which we'll talk about more next week, exams are a little bit different. You can't work on them together, and it's still everything is, yeah.
So the angles measurement doesn't count for the...
No, yeah. So, yeah, it's a good question because you're like, well, this only gives us like a 2. You tend to not limit it to angle because angles are oftentimes an approximate measure anyways. Although if you wanted to limit it to 2, that would be fine. I wouldn't say, no, you didn't give enough precision because this is, but yeah, angles are usually an approximation anyways. Because unless you like get out a protractor or a laser, like you're not giving any level of precision anyways. So usually do approximates with angles. Is that all right? Okay, so this week we need to talk about Newton's laws. And this is completely different from what we've been doing so far. It's not heavy math. So far we've been using a lot of algebra and have been working through some of these. This is not heavy on the math side. This is very, very light on the math side. And so what I want to just talk to you about is a little bit about Newton's laws and how they work. And there is a little bit of math, but not very much. So prior to Newton kind of synthesizing and putting together his thinking and publishing his findings and his thoughts and his math on motion, our idea of how objects moved, all of our ideas were wrong. They were just wrong. And in fact, if you talk to people, you find that people still don't really think in Newtonian thinking. We still have, I think unless you stop and you really think about what's going on, we still have a wrong idea of how things move and why they move. And so ultimately, Newton synthesized how objects move in three main laws. And so Newton's laws of motion. What are Newton's laws of motion? There's the first one, which basically says this: an object maintains its velocity unless forced to accelerate. And this force is a very, very important part of this law. So an object maintains its velocity unless forced to accelerate. What's my velocity right now? 0, right? I still have velocity, it just happens to be 0. And my velocity is going to remain 0 unless I am forced to accelerate. Like this, right? I force myself to accelerate, or somebody could come and shoulder check me or whatever, throw me backwards. Don't do that, it's not worth it. Because we'll talk about Newton's third law, and if you were to shoulder check me, whatever force you give me is going to go back on you. And I assure you it's not worth it. It's like hitting a moose, in your car. It's just not worth it. No amount of meat is worth hitting a moose. Don't do it on purpose. If you do it on accident, whatever. Did I ever tell you about when I moved to Ohio and I got my driver's license there? You had to read their driver's handbook. They had 4 pages in their driver's handbook about what do you do in the event that you hit a deer and you want to be the legal, rightful owner of that deer that you have now killed. 4 pages of their driver's handbook about how you go about being declared the rightful owner of that deer so you can take it home and eat it. Is that crazy? 4 pages. I read that and I was like, where on earth did I move? And actually the night before this, I had been in Walmart in Ohio, and somebody drove to Walmart in Ohio on a combine. Not like a tractor, like a small tractor pulling like a trailer, on a combine. If you've ever seen Cars, the bull, what is his name, Frank? That's a combine. I mean, this thing was huge. It was taking up literally like a quarter of the entire Walmart parking lot. Somebody drove to Walmart in their combine. And then the next day I read in the driver's handbook about 4 pages of how to get a deer declared your property so you can take it home and eat it. It's a strange place. If you have family in Ohio, pray for them daily. It's a strange place. I love Ohio. It is strange though. All right, so that's Newton's first law. So an object's going to maintain its velocity unless forced to accelerate. The second law, the force on an object is equal to the mass of an object multiplied by its acceleration. The force on an object, this is where we get a little bit of math, but it's like this equation here. X equals V naught times T. Algebraically, it's fairly simple. It's 1 multiplication. So the force on an object is equal to the mass of that object multiplied by its acceleration. So if you want to know how much force it took me to do this, you would just have to figure out what my acceleration is, right? How quickly I was speeding up, and you'd have to figure out my mass, which is about 138 kilograms. Now what you're thinking, you're like, what's a kilogram? It's a lot, okay? It's okay though, I feel okay about it. You don't have to feel bad. Did I apologize the first time we met that I oftentimes make fun of myself? And did I tell you it's okay if you laugh when I make fun of myself? Because I was with my youth group last night, and I made fun of myself, and they all felt very uncomfortable, which is very unusual because usually they laugh, but they didn't. They felt very uncomfortable. I think I kind of crossed the line a little bit, is I think what happened. And then the last law, the third law. And it basically can be summed up like this. If you kick a ball with a force of 6 newtons, we'll talk about what a newton is, the ball pushes against your foot with the same exact force. And this is why I said it's not worth it if you come and shoulder check me, because whatever force you exert on me is going to be exerted back on you. And if you're going to exert enough force to get me to move, it's going to hurt. It's going to hurt a little bit. Might hurt me a little bit, it's going to hurt you a lot. This is fun to do with my children. So I figured out a way in which I could play with my children while exerting very little effort. You know what I do? I stand there and I let them run into me. And they love it. They love it. All 5 of them, right? They think it's the coolest thing ever. They run as fast as they can. They jump into me. They'll put their head down and ram into me. And it requires very little effort on my part. If I'm getting really creative, I'll lay on the floor and basically tell them to try to move me, right? And then it's like, just chilling, and while they're trying, they're just having a good time. And they'll spend hours doing that. It's great. It's great. I also play with my children normally, so you don't need to, worry about their safety. But it's a great way. All right, so these are Newton's 3 laws. Are there any questions with Newton's 3 laws? Have you heard these before? You've done like a physical science class, or you've played around with these before. Maybe they're new, but you're like, okay, it makes sense, right? I watched SciShow for Kids, right? We were talking about Newton's laws. Okay, so to address this research framing question, I like to address these for you so you can write them in your notes. What are Newton's laws of motion? Basically, just write Newton's laws describe how and when an object accelerates. Again, it's Newton's laws describe how and when an object accelerates. One more time. Newton's laws describe how and when an object accelerates. You okay with that? And remember, acceleration can be negative. So if you're slowing down, you are still accelerating. Your acceleration is negative. Got it right? Okay. So let's talk about the first law in a little bit more detail. How does Newton's first law work? How does Newton's first law work? Let's create a little image for you. So imagine a grizzly bear lying on the ground. The only way that grizzly bear is moving, right? The grizzly bear's velocity is 0. The only way that grizzly bear is moving is if it decides to, or something really strong gives it a good push, right? And I put in parentheses, maybe another grizzly bear. Okay? The only way that grizzly bear is moving is if it chooses to, so it exerts a force on itself, or as if something else gives it a really good push. Otherwise, according to Newton's first law, that bear is going to maintain its velocity of 0 until it's forced to move. Okay? Until a force is acted on it. Make sense? Okay, now imagine this. So imagine a car driving at 65 miles per hour. Even if the driver doesn't hit the brakes, as soon as she takes her foot off the gas, that car's going to start slowing down, right? I don't know if you've experienced that, whether but if you've been in a go-kart or you've been on a riding lawnmower, if you've ever been on, or if you've been on anything, even on a bicycle, as soon as you stop pedaling, you start slowing down. And we're like, wait a minute here. According to Newton's first law, we should be maintaining the velocity unless forced to accelerate, right? So what's going on here? How is this describing Newton's first law? Why does a car start to slow down even if you don't hit the brakes? Why does your bicycle start to slow down once you start pedaling even if you don't hit the brakes? Yeah. Friction. Friction is a force. It's forced to accelerate. As soon as you take your foot off the gas, even while your foot is on the gas, friction is acting against your car. Which is why your gas tank doesn't stay full forever, unfortunately. Because it'd be nice, all you'd have to do if there were no friction, you just give it a little bit of gas to start it off, you get that velocity, and then you just, let that velocity be maintained as long as you want, right, until you hit the brakes and you stop it. But friction is a force. So as soon as you stop pedaling on your bicycle, you're experiencing that force of friction. And it is forcing you to accelerate in a negative direction, to slow down. You okay with that? So that's Newton's first law. An object's going to maintain its velocity unless it's forced to accelerate. And so if you're traveling in space, there's no friction. So then you get to this jump out of the space station, and you'll just keep going at whatever that velocity is until you hit something. Or hopefully you would be tethered to the space station if you ever get a chance to do that. So eventually the rope will, snap. You can pull yourself back in. Don't jump off into space, because that'd be terrible. Okay, so we okay with Newton's first law? So how does Newton's first law work? Just write to answer that question. Say you need to remember friction. But make it personal. Say, I need to remember friction. How does Newton's first law work? I need to remember friction. Because when you read that, you'll remember, we said friction was a force. So friction is going to be forcing you to accelerate. The faster you're moving, the more extreme that friction is. Which is why you feel it a lot more in a car. I don't know if you've ever felt that. You've been riding in a car, somebody takes their foot off the gas, you feel slowing down a lot more than on your bicycle when you stop pedaling. Okay? The faster you're going, the stronger the friction, the force of friction. Okay. Nobody has any questions? I told you this week is a little bit different. It's not a lot of algebra, it's not a lot of heavy stuff. It's just concepts. Okay. So how does Newton's second law work? How does Newton's second law work? Basically, on the initial slide, I told you the force acting on an object is equal to the object's mass times its acceleration. And this is what we're looking at. The force, F, acting on an object is equal to the object's mass, M, times the object's acceleration, A. Force is equal to mass times acceleration. F equals ma. I will tell you something, and you may not believe it, and you probably won't care, but you can derive every other formula we will ever use in this class from this one here. You can take this formula and convert it into every single formula we will use in this class. This is basically the hallmark, the core of physics. Force equals mass times acceleration. It's big. Newton's second law. You're like, why didn't he get this one on the first one if this one's so big? I don't know. Maybe it took him 2 chances to get something really good. The first one's good too, but this one's really good. This is like the core of everything that is physics. And so we measure force in units called newtons, not like the cookie, but a Newton named after, who do you think? Take a guess. Newton's laws, Isaac Newton, right? It's Newton's laws. They're all about force. The unit for force is named after him. Isn't that nice? That's so nice. I don't know what his family thinks about that, but I'm sure they appreciate it. I don't think Isaac Newton cares too much about it. Isaac Newton loved Jesus, just a great, also a theologian, so I think he's just kind of enjoying his eternity. But if he wasn't, he'd probably appreciate that we named the unit of force after him. And here's what a Newton equals. 1 Newton is equal to 1 kilogram meter per second squared. Because you have to keep in mind, force is equal to mass, which we measure in kilograms, times acceleration, which we measure in meters per second squared, right? Acceleration due to gravity, 9.80 meters per second squared, right? So 1 Newton is equal to 1 kilogram meter per second squared. Okay? So here's how this works. As the mass of an object increases, the acceleration due to the same amount of force decreases. So here's the deal. If you kicked a soccer ball, right? The acceleration on that soccer ball is going to be determined by how much mass that soccer ball has and how much force you put into your kick, right? Do you agree with that? So if you kick it harder, it's going to accelerate faster. If you kick it softer, it's going to accelerate more slowly. That make sense? But that's dependent upon the mass of the ball. So if you went to kick, say, a medicine ball, have you ever seen one of those medicine balls that's like 5 or 10 pounds and you use it for like doing crunches and you go to kick that like you're going to kick a soccer ball? Man, you better believe that thing is not going to accelerate as quickly as a soccer ball is. How many of you have kicked one of those medicine balls? Man, it is just, I mean, it doesn't, you could really hurt yourself, so don't do it. But it's not like kicking a bowling ball, right? although you get a similar idea there. And so what this is basically saying is if the mass of an object increases and you exert the same amount of force, that object is going to accelerate less because its mass is higher. Okay? Now, to kind of sum all this up, and something Newton really talked a lot about, is that the object is always going to accelerate in the same direction as the force acting on that object. Okay, so force is equal to mass times acceleration. If the force is positive, that is, it's in a particular positive direction, the acceleration is going to be in that same direction. Same direction. May I erase this? One of you is going to remind me to grab those note cards before you all leave, right? I know I remember now, but that doesn't mean I'm going to remember like 10 minutes from now. Okay? So one of you needs to remind me. Or all 9 of you can remind me. That's fine too. Okay. So let's do a couple of problems. What is the acceleration on an object that a 5.00 Newton force is pushing if the object has a mass of 5.00 kilograms? All right, what do we have? Somebody give me one of our measurements. Okay, so 5 newtons, what is that? What is 5 newtons a measurement of? Force, right? So force equals 5.00 newtons. Do we agree? Okay, what about another measurement? 5.00 kilograms, right? Do you see that number as well? And what is that? What is kilograms a measurement of? Mass. Awesome. Mass equals 5.00 kilograms. Okay? That's it. That's all we have. That's all we're given. So now let's talk about some tools. We have a tool that says the force is equal to the mass times the acceleration. Newton's second law. So I'm really excited about this. I hope you're, a little bit excited. We can rearrange this. Well, here, first let's ask, what do we want? What is this problem asking us for? I thought you were going to give us the answer. That was really exciting. What is the acceleration, right? The problem wants A. It wants acceleration. Well, we can rearrange this algebraically to solve for A. How would we do that? We want to solve for A. What do we do? We can't subtract A because it's being multiplied to the mass, right? What's the opposite of being multiplied to the mass? Let's divide it away. And if you divide mass away on this side, you better believe you got to do it to this side. Whatever you do to one side, you got to do to the other side, right? You can't let one side have all the fun, okay? You got to be fair. So what's mass divided by mass? If we multiply 3, we divide it away, what do you get? If you multiply 3 and you divide it, you basically did nothing. Do you agree? So these cancel, and we're left with that the acceleration is equal to force divided by mass. Do we agree? Okay, so we want acceleration. It's equal to force, which is 5.00 newtons, divided by the mass, which is 5.00 kilograms. And we get that acceleration is equal to 5.00 divided by 5.00 is what? It's just 1. But we'll maintain our same number of values, our same number of significant figures. And then you have to keep in mind, what is a newton? 1 newton is equal to 1 kilogram meter per second squared. Right? We had that on the previous slide. So what's a kilogram divided by a kilogram? Just 1, right? So we can cancel those out in the same way we canceled out mass here. And so what units are we left with? meters per second squared. Why is that good? What are our units for acceleration? Meters per second squared. Look at that. The core of physics. Force equals mass times acceleration. Using it to figure out if you exerted a 5 Newton force on an object that is 5 kilograms, it's going to accelerate 1 meter per second squared. That means every second its velocity is going to increase 1 meter per second. Okay, so every second its velocity is going to increase 1 meter per second. So initially it's 0, right? Assumedly, the object, but now we're pushing it. And so after 1 second, its velocity is going to be 1 meter per second. After 2 seconds, its velocity is going to be 2 meters per second. After 3 seconds, its velocity is going to be 3 meters per second. Right? Is that okay? Let's do another one. So, look at the only thing that changed. Instead of kilograms, it's grams. This is fun. This problem actually makes sense. My one with the basketball problem, it didn't make sense. I apologize for that. I was just like, let's use some numbers, and then little did I know that basketball player was going to hurl that basketball 200 feet. Which I've actually watched people do, making more than a full court length shot. But keep in mind that if you're going to do that, that ball's going to get way up into the air, right? So you can get that. Sorry. All right, so what do we have? Our force is still the same, right? We still have force is equal to 5.00 newtons. And now what else do we have? What else are we given? Yeah, mass is equal to 5.00 grams. Still have the same tool. Force is equal to mass times acceleration. We still want the same thing, right? We want acceleration. Which, that problem, we rearranged acceleration to equal force divided by mass. The problem is, we need to have our mass in kilograms. And why do we need our mass in kilograms? Looking back to this problem here. Why do we need our mass in kilograms? What is a Newton equal to? 1 kilogram meter per second squared. So we need our mass to be in kilograms, otherwise these units don't cancel. And we wouldn't just be left with meters per second squared. And now we're like, oh man, how do we convert? So we want A, but we need kilograms. Okay? We want A, but we need kilograms. So we need to figure out a way to do this. We need to use another tool. And that is 1 kilogram is equal to how many grams? Those of you that have taken some kind of a physical science class or some science background, maybe a biology class or anything else. 1 kilogram, how many grams is it? 1,000. 1 kilogram is equal to 1,000 grams. Meaning, if we want to go from grams to kilograms, 1 gram is equal to 0.001 kilograms. Right? So if we want our mass in kilograms and not in grams, we need to take our mass and multiply it by 0.001 kilograms per gram. Does that make sense? If 1 gram is equal to 0.001 kilograms, if we want to go from our mass in grams, we need to multiply it by 0.001 kilograms per gram. Now, if we put our mass in here of 5.00 grams, grams will cancel, and we'll be left with just what? Kilograms, right? And that's great, because what do we want? We want kilograms. So what we find is that 5.00 grams times 0.001 kilograms per gram, grams cancel, and we're left with 0.00500 kilograms. We want to maintain those zeros still because we don't want to lose them. And you're like, well, what about the zeros before? Those are just placing that 5. Okay, they don't count. So we want to maintain those zeros. Okay, so we want acceleration, which equals our force, which is 5.00 newtons, which is 1 kilogram meter per second squared. Do you agree with that? I just replaced newtons with kilogram meter per second squared. Since every newton is equal to 1 kilogram meter per second squared, we're going to divide this by 0.00500 kilograms. What do kilograms do? They cancel out. Right? And then so what we'd end up getting is that our acceleration is equal to 1,000 meters per second squared. Instead of 1 meter per second squared, our acceleration is 1,000 meters per second squared. That kind of makes sense because this mass is 1/1000th of our previous mass. Instead of being 5 kilograms, it's 5 grams. Is that okay? We'll have some more time to talk some more about this next week. Next week we're going to do Lab 2. So we'll talk some more about Lab 1 that you've hopefully been working on up to this point. We'll do Lab 2, which is going to be fun. We're going to drop stuff off the second floor. We're going to calculate how much time it takes to drop. We're going to figure out if gravity is actually acting at 9.80 meters per second squared here. Because the thing is, it varies with where you are, the elevation. The closer you are, anyways, we'll do that. We'll play around with it. We'll do some cool stuff. And then we'll also do, instead of just dropping it, we'll do a little throwing things. It'll be fun. We'll wait till somebody's walking by and we'll drop it on them. We won't do that, but we could. It'd be fun. All right, so Newton's third law. Just real quickly, I want to talk about this a little bit, and we'll talk about this more next week. So I want you to think about a time when you kicked a heavy ball. Those of you that have kicked a medicine ball. Did it hurt? Could you at least feel the object? Even if you kicked a light ball, like just kicking a soccer ball, could you actually feel it? How many of you have kicked a soccer ball? Okay, we got everybody. Good. You can feel it, right? You can at least feel it even if it doesn't hurt. And the reason for that is if you push an object with a force of 5 newtons, it pushes back on you with a force of 5 newtons. The same force you exert on it is exerted back on you. If you kick a soccer ball, that soccer ball feels the force from your foot feels that same force. So the harder you kick a soccer ball, the more you're going to feel it. Which kind of makes sense. If you just kind of tap it, you don't really feel it at all. If you really rear back and give it a good kick, you feel it a lot more. You're going to like the homework problem on this one. I create a scenario in which you jump into a sheet of glass. You're going to like it. It's really not that complex, which may also make you like it. And then so if real quickly you want to write down an answer to this, and again, we're going to come back. We're going to talk more about this next week. We'll talk about Lab 1 next week, and then we're going to do Lab 2. It's going to be lots of fun. Also, we'll talk more about the exam next week. But how does Newton's third law work? Just write this. Whatever you give, you get. Whatever you give, you get. If you give a soccer ball as much as you can possibly give, you're going to get back from that soccer ball as much as it can possibly give. Well, compared to what you gave it, right? You get what you give. You get what you give. You get what you give. You give, you get what you give. Get what you give. That's kind of fun to say. You get what you give. You get what you give. Have you ever seen The Terminal with Tom Hanks? This is in no way an endorsement for the movie. In fact, I haven't seen it in a long time, so I don't know whether it's a great movie at all. But he has a hard time learning English, and he keeps trying to say a bite to eat, but he says eat to bite, eat to bite, eat to bite, eat to bite, eat to bite. And that's like the only thing I remember from that movie. You get what you give. You get what you give. You get what you... Man, I can't stop saying that. It's so much fun. You get what you give. All right? That's all I have for you. Thank you for your time and for your attention and your focus and your enthusiasm and your love for all things physics. And we'll meet back here, same time, same place. If you have trouble working through the homework problems, because some of them are philosophical, just kind of thinking problems, let me know. Send me an email. We can talk through some of these. All right? Cool. Thank you all for coming. Have a safe trip. Use your shirt to mask your mouth as you breathe outside there so you don't inhale too much smoke. You are very welcome. You learning? Good. Bye. Oh, the cards! The cards! Wait up! Wait up! Don't leave! Don't leave the cards! Cards. So it's your login, your username and your password, and then a little note of encouragement. So this is you, right, Colby? And this is you. And you're welcome. This is you. You didn't put your name on it, but I assumed. Oh, you put it on the back. No, that's fine. Okay. Now let's see if I can do this right. Malachi. Thank you for reminding me.
Oh no, she remembered.
She remembered nice, and she was going to answer our acceleration question too.
Thank you.
Yeah,
Sorry,
you're
I
very welcome.
whispered.
No, I get it. Yeah, I get it.
Thank you.
Yep.
So I might be a little late next week.
Okay.
I've got the PSAT